Okay, next up we'd like the Lewis structure for CH2O. Let's count our valence electrons. 4 plus 2 plus 6. 12 electrons to move around. We know carbon will be our central atom. So the hydrogens, let's attach it to it. And then lastly we have the oxygen. Let's put in all of our octets and see if we have enough. 2, 4, 6, 8, 10, 12, 14. So we have 2 extra electrons here. And we're going to fix that by having a double bond instead. And this just makes sense because carbon likes to have 4 bonds and oxygen likes to have 2. So just give them both what they'd like. Count our formal charge again. And so on the hydrogens, we're going to have 1 minus 1, 0. On the carbon, we're going to have 4 minus 0 minus 4, 0. And then lastly on the oxygen, we will have 6 minus 4 minus 2. And that is also 0. So our formal charges all make sense because the net formal charge is 0. And our valence electrons are all accounted for. So this is a correct Lewis structure. And so now we go about counting the steric number around carbon so we can determine the geometry. And so we have 1, 2, 3 groups attached to it. So it's going to be 3, and none of them are lone pairs. So all bonding pairs, and so its notation would be AX3. If you go to the VSEPR chart, we just go to the total domain, steric number 3, 3 bonded atoms and 0 lone pairs. And so what that is going to look like is we will have C attached to O, and then the H and the H. And this is what it's going to look like. It will be trigonal planar in both its geometry, so it's electronic geometry, and its molecular geometry. Now we need to determine its electron geometry. We found that it is trigonal planar. And now we'd like to find out what the strongest intermolecular force this molecule would exhibit. And so let's just list down these intermolecular forces so that we can determine their various strengths and then determine which ones this molecule actually has. And so we have London dispersion forces. These are a form of van der Waals forces, and these are the weakest. And they're caused by temporary dipoles forming. And that's just going to be because of the electrons randomly being in places that would tend to form a dipole. We have dipole-dipole forces. So these occur in all molecules, including nonpolar and polar. We have dipole-dipole forces, and these are pretty strong. They are only in polar molecules, and they're a result of the net dipole moment being non-zero. And then lastly, we will have hydrogen bonding. And this is caused by a very high difference in electronegativity between hydrogen and nitrogen or oxygen or fluorine, I believe. And it is the strongest. And that is just caused by, because the difference in electronegativity is so high, the electrons are much, much closer to the nitrogen, oxygen, or the fluorine, and that gives a very high partial positive charge to the hydrogen and a very high partial negative charge to the oxygen, and that allows it to pull ionic species apart and isolate them. And so we just need to note which ones are possible in what we have. So London dispersion are possible because it's possible in all molecules. Dipole-dipole, in order to determine whether it's possible, we need to determine whether this molecule is polar. And so we begin by drawing our dipoles. And I'm just drawing these based on the electronegativity of these specific atoms. And so carbon has a higher electronegativity compared to hydrogen, and oxygen has a higher electronegativity compared to carbon. And so what that means is that these two, since they're equal, the angular components will cancel out, leaving with the dipole pointing up. And you'll also have the dipole pointing up towards the oxygen. Clearly, these two cannot cancel, and it'll be non-zero, meaning that the molecule is polar. So that means that dipole-dipole forces are possible. Next up, let's check on hydrogen bonding. So when it occurs when we have a high difference in electronegativity between hydrogen and nitrogen, oxygen, or fluorine. We do have hydrogens, but they're not attached to this oxygen. They're attached to carbon instead, which isn't listed here. The difference in electronegativity isn't strong enough to cause hydrogen bonding. And so this is not possible. So this isn't going to be in our molecule. And so between these two, which one is stronger? And that's going to be dipole-dipole. So dipole-dipole will be the strongest intermolecular force this molecule is going to exhibit. And then lastly, we are asked for the molecular geometry. And we've already determined it. It's the same as the electron geometry because of the fact that they're no lone pairs. So it's going to be trigonal planar too.